Hi, I'm Sean Brady, and we're going to talk about complexity theory and engineering failure. And we're going to do so by taking the example of the Florida International University bridge collapse. Complexity science gives us a totally different way of looking at engineering failure, and that's what we're going to explore today. So we're going to begin by going to the 15th of March 2018, and we're going to go to Miami, just outside the Florida International University. Under construction at the time was this bridge. This was a bridge that looks like a cable-stayed bridge, but it's actually not. That's largely for architectural purposes. The key bit we're interested in is this piece here, the main span. Now, at the time of the incident, the main span was really the only part of the bridge that was in place, and it was over a highway that was open to about 8 lanes of traffic at the time. This is a concrete structure. It had actually been built in a yard beside the highway and then moved out over the highway and put into position. Now we're going to start by looking at some dash cam footage, and this is distressing footage. This is a vehicle that is parked beside the highway where the Florida International University bridge is, and you're going to see the vehicle turn out on that road, and you're going to see the bridge in the distance. And this happens incredibly quickly. The bridge collapses. Now we're going to watch this again with slow-mo. I want you to take a look at the left-hand side of the bridge. You'll see that over on that side there's a crane, there's some construction work taking place. And this is where the incident is initiated, or the failure is initiated. You'll see the bridge collapse and hinge almost downwards from that point. Now, there were workers on the bridge at the time of the failure, and one of those was killed. But because the road was open to traffic, the lights were red, the cars were backed up behind that red light beneath the bridge, and when that bridge collapsed, it killed 5 occupants in the vehicle. So 6 people died in this tragedy overall. Now, how did it happen? Well, to pull that apart, we need to go back and take a look at the structure itself. So this is a concrete truss bridges. Now, truss bridges usually have 2 sets of trusses, these vertical and diagonal members that run down each side. This bridge had only 1 line of them down the center. It was a pedestrian bridge. You'll see the bridge deck on the bottom. You'll see that single line of truss members above it, and then you'll see the canopy above that. Now, we're really interested in this left-hand side of the bridge where the failure initiated and began the progressive collapse of the bridge. The key members to look at here are member 12, which is that vertical member, member 11, which is the diagonal member, and it's where they both join to the bridge deck that's important. So this member 11 12 to bridge deck connection is where the failure was initiated. Now, when you have a look at some of the footage they have of the collapse, and here you can see some of the footage. We've got a freeze frame. We've got each of those members in place. Have a look at the left-hand side, member 11, 12, to where they both join the deck, and you'll see we got an explosive failure. That joint basically exploded. You see a cloud, essentially, of concrete dust come from that place. Now, once we start that failure, this bridge has got no redundancy because it's got that single line of truss members down the middle. So once we fail that joint, the bridge begins to rotate. It fractures the canopy, it fractures the deck at that location, and from that point forward, it forms what we would in engineering call a hinge, and it just rotates downwards. And you'll see even from this still that the rest of the bridge is intact. And then the bridge hits the highway and the vehicles below. And the right-hand side of this bridge is still largely intact, even at this point. Now, the speed of this collapse was incredible, and it was what we call a brittle failure, and it happened in about 0.4 of a second. So less than half a second was all it took for this failure to be initiated until complete collapse. So why did the bridge actually fail on the day? Well, the bridge failed on the day because there was workers working on top of the bridge, and they were reapplying post-tensioning to this key member 11 to 12 deck joint connection. Now, we don't want to get into a discussion on post-tensioning and what it is, but fundamentally what it comes down to is you apply a tension to a rod, and they were applying a tension to the rod in this case to close up cracks in this key member 11 and 12 deck joint connection. Now, afterwards, the National Transportation Safety Board, who investigated the failure, said this was never going to happen. They were never going to be able to effectively close up these cracks because these cracks were too bad. But it was the application of this big tensile force to that damaged joint that caused the joint to explosively fail and collapse the bridge on the road below. But where did these cracks actually come from in the beginning? Well, the story of the cracking of the Florida International University Bridge goes right back to the early days of the bridge. So the bridge was cast in a yard just off the highway, like we discussed. And what they do is they put up all the formwork, they pour the deck, they wait for the deck to essentially set, then they pour the truss members. After they've poured the truss members, they then go and pour the canopy on top. They let some time pass, and that's for the concrete to gain strength. And then when they deem that the concrete has got enough strength, then what they can actually do is take off all the formwork. Now, when they take off all the formwork, you've basically got this bridge sitting in the casting yard, spanning from one side to the other. And this is the first time in this bridge's life it's ever had to carry its own weight. But during the removal of the formwork, they heard cracking sounds. And they discovered there was multiple cracks on the bridge, some of which were around member 11 and 12. Now, in concrete structures, we get cracking. It's a normal part of concrete structures. The way we manage that is we make sure the cracks haven't got too wide. Now, the particular number that matters for this bridge is that the cracks can't exceed 0.4 of a millimetre in width. Now, if you're wondering how small 0.4 of a millimetre is, it's basically the thickness of your nail on your little finger. So it's very, very small. But while this was the requirement, what they found not only from the early days, but as time progressed, that these cracks were not smaller than 0.4 of a millimetre, and they started to grow over time. Then this span was taken, it was moved out over the highway, and it was placed in the position that we saw in the beginning. And after that particular move, these cracks really started to grow. Here's some photos that were taken in the days and weeks leading up to the collapse. You can actually see that measuring tape is stuck down into one of the cracks in the concrete. This is the critical joint, the 11 and 12 to deck joint connection, and we're looking in on the side of the bridge here, and you can actually see that not only is the cracking really bad, but we're starting to get spalling. We're actually starting to knock pieces of concrete off the bridge due to whatever stresses are taking place at this joint. This is a schematic that was done by the NTSB to show the extent of the cracking leading up to the failure. The NTSB report said that this cracking was evidence of a bridge that it was screaming that something was wrong with itself, yet construction continued. Now, it would turn out that this particular joint, among some other problems, but we're just going to focus on this joint, it would turn out that this joint was under-designed. In other words, it wasn't strong enough for the loads and the actions it was meant to carry. And because it wasn't strong enough, that's why we start to see all this particular cracking. But how do we design a bridge in which we make a fundamental design error in a critical connection? And why, when we start to crack up this bridge, do people not go back and check that everything seemed to be okay? You know, after all, we've got a process for checking. Now, to understand why this is taking place, we need to actually go and look at the parties who were involved in delivering this bridge. So the bridge was being built for the Florida International University. Now, working with them was the Florida Department of Transport. The funding model that was in place meant that the Florida Department of Transport had to have oversight on some of the technical aspects of the project. Florida International University awarded the contract, which is a design and build contract, to MCM contractors. MCM contractors then went and hired a group of designers called FIG to do the actual design of the bridge. Now, we're going to spend a bit of time talking about this, but the design had to be peer reviewed. It had to be checked by another engineering firm. And the firm that would do that was a firm by the name of Louis Berger. There was also other parties involved. There was a group called Structural Technologies, and there was also a group called Bolton, Perez and Associates. And their job was to work with Florida International University to make sure the bridge was designed and constructed properly. But the key bit we want to focus on here, and we could talk about many aspects of this failure, is the role of Louis Berger. We've just talked about the fact that this key joint, the member 11 to 12 to deck joint connection, was under-designed. But how was that missed? How was this design error missed by the very people who were meant to be doing the peer review? This is where it's really useful to talk about the concept of complexity. Well, what's complexity? Well, complexity is really the study of complex systems, which I'll admit is not exactly making it easier to get your head around what we're talking about here. But the best place to start here is with an example. What's a complex system? A really good example of a complex system is the economy. You know, we like to believe we understand the economy, that we can predict what the economy will do. And sometimes we're not bad at that. And sometimes the economy behaves in a way that we understand and is reasonably predictable. But then there's times the economy doesn't work like that at all. We have booms, we have busts, we have very unpredictable behavior. So what's going on in a system like this? So when we talk about complex systems, what I really want you to do is think about how you think about systems. This is about asking how systems fail. Now, the easiest place here is to not actually talk about complex systems first. We'll come to that. Instead, it's more important to talk about Newtonian thinking. So what's Newtonian thinking? Well, Newtonian thinking is the way most of us, particularly if we think we're rational, like to think. Now, where does it come from? Well, it comes from Sir Isaac Newton, who gave us the laws of motion, and he gave us calculus and many, many other things. He also gave us a way of thinking about the world. Now, we could spend quite a bit of time talking about Newtonian thinking, but there's a few aspects that are worth sort of running through here. The first one is Newtonian thinking is deterministic. And what does that mean? Well, it means that if we understand the rules of a system and how a system works, we can predict what that system's going to do. If we want to understand where Jupiter is going to be 2 weeks from now, we can actually sit down and do the calculation. We can determine where Jupiter is going to be. In other words, there's a sort of a mechanical nature to Newtonian thinking and systems. And you'll probably have heard the term the clockwork universe, where we can work out how everything is going to behave because we think of it as this finely tuned watch almost. The second concept in Newtonian thinking that's really useful is that it's causal. And what that means is that we tend to assume there's a sort of a symmetry between cause and effect. Little effects are caused by little causes. Big effects are caused by big causes. There's a symmetry. The interesting thing is, though, that while that may apply to Newtonian systems, doesn't necessarily apply to other systems. And the final concept, which is probably one of the most important ones for us here, is the concept of reductionism. Now, what is reductionism? Well, reductionism is the belief that if you want to understand how a system works, all you need to do is break that system down into its individual components or its individual agents. And then, by understanding what each component or agent does in a system, we can predict and understand the behavior of the system as a whole. In other words, once we understand the components or agents, we understand the system. Another way to think about this is that the system is the sum of its parts. This very reductionism causes us a problem. Now, what is the problem? Well, let's talk about the problem of reductionism through an example. Let's take an ant colony. Ant colonies are very sophisticated. They are capable of very sophisticated behavior as a colony. Now, let's say we wanted to understand how that colony worked. Well, we'd never understand that colony if all we did was catch a single ant and study it and study it and study it. We might learn a hell of a lot about the ant, but we wouldn't learn very much about how a group of ants work together in a system. Ants themselves are not that impressive, but when you put them together in a system, they can do incredibly impressive things. So suddenly, reductionism doesn't help us understand how an ant colony works by just studying the ant. Another really good example is, let's say you want to understand how your garden works. Well, you can go out there with a net and you can catch all the species of animals and you can pick all the species of plants and you can pin the animals to boards and you can study them. And you'll learn a lot about the individual animals and plants, but you'll almost learn nothing about how your garden as a system, as an ecology, actually functions. Reductionism doesn't work for certain systems. Doesn't work for so-called complex systems. And the reason it doesn't work for complex systems is because of a concept called emergence. So what is emergence? Well, emergence is when the agents or the components of a system come together to produce behaviour that is not designed into the system. In other words, a complex system is more than the sum of its parts. While a simple system is the sum of its parts, a complex system is more than the sum of its parts, and it is because of this concept called emergence. Now, emergence should hurt your head. There is a wonderful quote by complexity scientist Don Farmer where he says, "What does it really mean to say that the whole is greater than the sum of its parts?" It's not like magic, but to us humans with our crude little human brains, it feels like magic. Somehow, by constantly seeking mutual accommodation and self-consistency, groups of agents manage to transcend themselves. This is a very powerful concept. When we put these agents and components together, the way they seem to interact with one another produces something that's more than the sum of its parts, produces emergence. Now, there's a wonderful example of this, and I'm sure you've all seen this sort of footage before. But this is known as a murmuration of starlings. And what we have really is a group of starlings that are flocking together. And the incredible thing about this is we're getting organized behavior. The starlings are able to coordinate with one another to produce behavior that we would say is organized. Now, how is this happening? How is this taking place? Is there one boss bird who's in charge, who dictates what all the other birds are going to do in this dance in the sky? Or what is happening here? Well, to explore this, what we're actually going to do is going to build a model. We're going to attempt to build a model of starlings flocking. So here we've got, I want you to imagine for a moment, this is a model of a sky. And we've got hundreds of starlings in the sky. And this is a wraparound world. If a starling flies through the top, it appears in the bottom. If it flies out the left, it appears in the right. Now, the interesting thing is that we have randomly placed the starlings in the sky here, and we can set them flying. And as we do, it's pretty boring. The starlings are flying in their own direction, and it's pretty boring because they're not interacting with one another. And what one scientist, a guy by the name of Reynolds, came up with was, what happens if we make them interact with each other? What if we give them some rules? And he came up with 3 simple rules. And the first one of these is called alignment. And that means that a bird tends to turn so that it is moving in the same direction as nearby birds. The second point is known as separation. And in separation, what that means is a bird will turn to avoid another bird that gets too close. And finally, the last rule is cohesion. And what this means is that a bird will move towards other nearby birds unless another bird is too close. Now take a look at these rules. They're incredibly simple. The other thing about these rules is they are local. In other words, they're rules that dictate how birds interact with each other or how starlings interact with each other at a local level. They're not global rules that we would think about in other systems. Now, the really interesting thing is we can apply these rules. So here's the model we saw earlier of our sky and our starlings, and we can come along and we can apply the rules about now. And almost instantly, you start to see a change in the behavior as the starlings begin to interact with one another. And slowly, you start to see behavior that is similar to the murmuration of starlings. In other words, the starlings are self-organizing. And this is what's really interesting. We never told them to flock together. We just give them 3 simple rules, but somehow out of those 3 simple rules, we get self-organization, and in addition to self-organization, we get flocking. Flocking is the emergent behavior. We never told them to flock, yet they did so. And this is what we see in complex systems over and over again. You can have simple rules that are only local between agents, but from that you can get self-organization emergent behaviour, and complex behaviour. Now, the really interesting thing here, which is really important to disconnect your head from cause and effect, is that the effect, the outcome here, the emergent behaviour, can be quite complex, but the rules, the underlying rules that produce that behaviour, can be incredibly simple. In this case, it was only 3 rules. But these 3 rules were what dictated the interactions between the starlings. And this is the key to understanding complex systems. Complex systems are the sum of their components and agents and their interactions with one another. This is what is so different to a simple system. You can break a simple system down to its components, and by studying those components you can understand the system, but you can't break a complex system down to its components and agents and hope to understand that system, because you're ignoring the interactions. This is why reductionism fails when we apply it to complex systems. We ignore the interactions, and that's where we go wrong. If we really want to understand how complex systems work, we need to look at the interactions and treat them just as importantly as we treat the components or agents in that system. So, with that, let's go right back to the Florida International University Bridge and take a complexity science lens at looking at the failure, which of course means looking at the interactions between the agents, or in this case, the parties in the system. Now, as I said, we could focus on many aspects of this failure. We're going to fundamentally focus on the role of Louis Berger and the interactions between Louis Berger and other parties within this complex system that was delivering the project. Now, we need to go back before the failure. We need to go back to 2016, when this job was in its very early stages. Now, Florida Department of Transport were involved, like we talked about, and Florida Department of Transport said that in the design and construction of this bridge, the design had to be peer reviewed. That was a fundamental requirement under the contract and the funding model that they had. Now, the good news is that if you want to do a peer review on a bridge, it's actually set out, and it's set out in the Florida Department of Transport's plans preparations manuals. And the important thing for us here is that when you go and do a peer review, the scope is already defined of that peer review, and it's defined in the plans preparations manual. So as we know, the job gets awarded to MCM contractors. They in turn engage FIG to be the designers of the bridge, and the next question remains at the beginning of this job is, well, who's going to be the third party that does the peer review? And the Florida Department of Transport require that the people who do this peer review are a third party, they can't be involved in the project, and they have to be pre-qualified with the Florida Department of Transport to actually do the work. So, who did FIG pick initially, when they were putting their bid together, to do the peer review? Well, they chose themselves. Now, sure, it was a different office, but they basically fundamentally decided when they were putting their bid together that they would check their own work, and that obviously would have had an effect on the bid price. Now, they get awarded the job. We fast forward a number of months. We're in a meeting with the Florida Department of Transport. FIG mentioned that they're doing the peer review of their own design, and the Florida Department say, no, you're not. And they force FIG to go out and get a third party to do this review. But of course, this puts FIG in a bit of a quandary, because they're in a hard dollar contract with MCM over the work. They hadn't planned to go out and pay someone else the money to do the peer review. They were going to do it themselves. But they were now forced to do this. And they were forced to do this because of the interactions between the parties. FIG put the peer review out for tender. They put out a call for bids, and this is when Louis Berger, who we've heard about before, enters the story. Louis Berger said, good news, we are pre-qualified with the Florida Department of Transport to do the work. And we will do it in accordance with the plans preparations manual. We're going to build our own models. It's going to be quite a sophisticated peer review, and the price for doing that is $110,000. Okay, so they get that bid, but FIG also got other bids as well. They got another bid for $85,000 and $63,000. Now, put yourself in FIG's position. And think of the interactions between you and MCM. You're there, you weren't counting on spending this money at all with a third party. Which of these do you think you're going to choose? The pressure to choose the cheapest one must have been intense. Now, Louis Berger seems to have had an understanding that there was a problem at this stage with their bid. And they went back to FIG and they said, look, before you make a decision, just be aware we're going to do a very sophisticated peer review here. We're going to build our own models. And we would love if you came back to us and give us a chance to put in our best and final offer. Now, we don't know exactly what transpired between this point and the work being awarded to Louis Berger, but what we do know is that the original bid from Louis Berger, which started out at $110,000, got slashed to $61,000, $2,000 less than the cheapest bid FIG had received. Not only was the money slashed from $110,000 down to $61,000, but the 10-week program to do the peer review was slashed to 7 weeks. Now look at the interactions between these parties. So you have Louis Berger, who planned to take 10 weeks and $110,000 to do the work, but now what's actually happening is they're going to do that work for FIG for a considerably less price and a lot less time. But despite this, FIG were quick to remind Louis Berger that the scope remained the same. The scope, after all, was set out in the plans preparation manual. So while we've had a reduction in time and money, we've not had a reduction in scope. And again, if we go back to the interactions between these parties, imagine what happens next. Now, I'm not excusing any party's behaviour in here or the requirements of what each party was meant to do. We're merely taking a complex systems view and say, if we look at the interactions between the parties, what emergent behaviour do we believe could result here? Now let's look at what eventuated from the interaction between Louis Berger and FIG. Now, two things really matter here. The first of these is that Louis Berger were meant to, under the plans preparation manual, to check every stages of the bridge's construction. And this bridge went through several different stages of construction. It was formed in that yard, it was then transported out, placed over the highway, and then the backspan was added to it, and then the pylons and the cables would be added to it. And Louis Berger were obliged to check each of these designs to make sure that they were okay. Louis Berger didn't do that. Instead, what they did was they only checked the final design of the bridge, the final design for when the bridge would be in service. And of course, we never got that far because the bridge collapsed at an earlier stage. Now, the second area is that the plans preparation manual means you have to check the design of the bridge. Is all its members okay? Is all its connections okay? It would transpire that Louis Berger checked the members and concluded they were okay, but they never checked the connections. And of course, as we talked about earlier, it was this critical member 11 to member 12 to deck joint connection that was under-designed. The loads and actions on that joint were way higher than its strength to resist those loads and actions. But this was missed because Louis Berger never checked the design of the connection. And afterwards, in interviews with the NTSB, Louis Berger personnel made many statements along the line of, there was simply not enough money in the budget or time in the budget to do these sort of checks, despite the plans preparation manual requiring them to do so. And what you see is that regardless of the requirements of each of these parties within this complex system that was delivering this bridge, the interactions between those parties had a bigger impact on their behaviour than some of those overall responsibilities. In other words, we had emergent behaviour related to the interactions that made the project unsafe. And we see this again and again. Here's a wonderful graph that was completed by some researchers in 2014. And what they did was they looked at the factors that are important in preventing structural failures in a project. And fundamentally, the easy way to read this graph is the taller the bar on this graph, the more important it is as a factor in preventing engineering failures. The interesting thing is when you go and you talk to engineers and you say to them, what do you think is the most important factor in avoiding failures? They will say technical competency. And as you'll see on this graph, technical competency is important, but it's not the most important things. The 4 most important things on this graph are communication and collaboration and risk allocation and control mechanisms. Who manages what risk and what control mechanisms do you have in place for doing so? In other words, this study shows that the most important thing in avoiding structural failures is related to the interactions between the parties. We see the same thing again and again in these sort of engineering failures. And what we see is that the interactions, the local interactions, just like our starlings, has a major impact on how parties will behave. What a complex systems thinking lens gives us is it gives us an ability to step beyond simply looking at what the components or agents in a system should or shouldn't have done. And it makes us look at what was the interactions between those agents and components, those local interactions. Because what complex systems theory tells us is that those local interactions will ultimately produce emergent behaviour. And that emergent behaviour may be quite different from what we hoped to design into the system. Thank you.